Welcome back to differential equations. We've been talking about the different forms that our differential equations might take. The whole point in a differential equation is to model something that happens in the real world, at least for our purposes. And we talked about our exponential growth or exponential decay model, and this is often used for unconstrained population growth or radioactive decay. So, for example, we might be told that carbon-14 has a half-life of about 5,700 years. And we want to write the differential equation corresponding to this and write an equation which gives us the quantity of carbon-14 present in a system given an initial amount. So our differential equation is going to look like dx dt is equal to lambda times x. We can solve this using separation and get that x of t is equal to some constant e to the lambda t. We're solving that using whatever method we want to. Now, given the information that it has a half-life of 5,700 years, at t equals 5,700, this means whatever we start with, our c value, we're going to have half of that left. So 1/2 c is equal to c e to the lambda times 5,700. The c cancels out, and we get that lambda here is about negative 0.00012, which allows us to refine our differential equation to dx dt is equal to negative 0.00012 x. And our solution is x of t, our one parameter family of solutions, is some constant e to the negative 0.00012 t. And this allows us to model how much carbon-14 is in the system or in the bone or whatever for any time t and given an initial amount. The problem is, this isn't the whole story. Carbon-14 doesn't just exist as a specific quantity that was set, pardon the pun, set in stone from day one of the universe, and it's just been decaying ever since. Carbon-14 decays into nitrogen-14, but boron and nitrogen both decay into carbon-14, and carbon-19 decays into nitrogen, and beryllium decays into boron, which then decays into carbon-14. So there's a whole chain here. So it's not enough, really, if our goal is to model the real world scenario of exponential decay, radioactive decay, it's not enough just to say, oh, carbon-14 has a half-life of 5,700 years. What we need to be considering is, yeah, carbon-14 might decay into something else, or let's use uranium-238 now. If we're considering the uranium-238, yeah, this decays into something else. So the amount of uranium is decreasing proportional to its quantity. But uranium-238 decays into thorium-234. So whatever we gained from uranium, we are now also losing, because thorium itself decays. We're also losing some amount of, based on the amount of thorium we have. And then thorium-234 decays into palladium. So that would be a dz dt. Now we picked up some from thorium, so we got lambda 2y, but then we're losing however quickly our palladium is decaying. Now, this is palladium 234, which decays back into uranium, but uranium 234 now instead of 238. So this is a whole chain, right? So what we end up with is, if we want to model the complexity of actual radioactive decay, it's not enough just to have a single differential equation. What we actually have is a system of differential equations. So it becomes important for us to have methods of solving systems of differential equations. Now, we're going to let that sort of steep in the back of our minds for a little bit. And let's consider a different scenario. So that was radioactive decay. We've shown radioactive decay. Yeah, you can model it as a single differential equation, but that doesn't really get to the complexity that we need to. Another example of a differential equation that we dealt with was a mixture differential equation, right? We had a vat of a chemical salt water, and we had salt rushing in, and we had salt water rushing in and salt water leaving. And this was our rate in minus rate out. The amount of salt in the container was equal to the rate in minus the rate out. Well, that's all well and good if we have one container. And again, we're assuming that the container is well mixed. That is, the concentration of the chemical here is the same as the concentration of the chemical here. We have to make that assumption, or we're in partial differential equations land. But what if we have two vats of chemicals, right? We have salt water coming into this vat and then moving from this vat into another vat, which is then pumped out. And then we have maybe some pump going back and forth between the two. So this is a much more complicated system, right? This system might look something like, if this is vat 1 and this is vat 2, then we might have the amount in 1 over time is equal to, I don't know, some quantity negative 2 over 25 A1. So we've got our rate leaving A1 plus the rate coming in, which might be constant, plus the rate coming back from A2. So here, this would be our negative 2/25. This is the amount leaving A1. If we assume that that's moving this direction, this is the amount coming back in from A2. That would be 1/50th. And then we have some constant amount coming in per unit time. And then A2 over time. Well, we've got stuff coming in from A1 at a rate of 2 over 25. That's its input. And then it's got stuff leaving, going back to A1. So it's losing whatever it's feeding back into A1. And then we've got some amount leaving it as well. So we've got K2 here. So again, what we're seeing here, the takeaway here is, yeah, we can model simple scenarios with a single differential equation, but it's not that hard to imagine scenarios where our single differential equation becomes no longer representative of the real world scenario that we want it to represent. The example that many textbooks love here is a predator-prey system. Or a competition model. Some textbooks just arbitrarily call these rabbits and foxes. And the idea is, if there are no rabbits, the foxes are just going to die off. So the rate of change of the foxes over time, this can be modeled with exponential decay. And if there are no foxes, then we can talk about the rate of change of the rabbits over time. Well, rabbits are just going to at least grow in the short term exponentially, though we know that that's problematic because that ignores carrying capacity. But in the short term, we can consider exponential growth. But if they're kept separate, right? There's no rabbits in the fox habitat, there's no foxes in the rabbit habitat. But the moment we sort of take this out of the zoo and start putting it in the quote unquote real world, if you will, then we might have, using X's and Y's for rabbits and foxes. Well, here, X here is the foxes, arbitrarily using X as foxes and Y as rabbits. Then the foxes left to themselves are going to have exponential decay, but they get helped when there are rabbits. Some interaction term, they get helped by the presence of rabbits. And then the rabbits themselves, perhaps D is a poor letter to use here. Call it E, parameter E. The rabbits by themselves are going to experience exponential growth, but then they are harmed by the presence of foxes. So they are losing due to the interaction, and foxes are gaining due to interaction. Again, the point of the system, or the point here is, we can represent simple scenarios using single differential equations, but the moment we try to represent a real world scenario, we have a problem. We need a system of differential equations. Okay, that'll take us to the end of today. We just want to acknowledge that there are, these are great for simple situations, but ultimately we want to get to the point where we can solve systems of differential equations, because most things in quote unquote the real world are in fact far more complicated than can be solved with just a single differential equation. Even the most basic of our examples, where we have radioactive elements. I'll see you next time.